Okay, so after looking at the disk, we now take a look at the code. On the cone surface, x3 cubed is equal to x1 squared plus x2 squared. That is coming from the simple fact that if you take a point on the x plane or xy plane, and then so you just find out that if you take a point on the xy plane, you can easily see that on the x3 squared is equal to x1 squared plus x2 squared, given that x1 plus x2 squared is less than 1. So the radius vectors contained in this region is psi, rho, phi. So in this region, on this cone surface, you have rho and phi are the variables on this cone surface. The theta is constant at pi over 4, so theta remains at pi over 4. So if this is the spherical vector, you just have that everything is remaining unknown except theta, which is at pi over 4. So and it's contained within the surface for 0 to root 2. So rho starts from 0 and it ends in root 2. Theta starts from 0 and it ends in 2 pi. Sorry, phi starts from 0 and ends in 2 pi. And then the two surface vectors, as usual, we get the surface vector by differentiating the surface, 2-parameter surface function, differentiating with respect to rho and differentiating with respect to phi. When we differentiate with respect to these two, as we did before, so we get the two surface vectors and we take the cross product of those two surface vectors, we get the vector perpendicular to the surface, the cross product of which gives you the normal to the surface. So this is the same kind of thing. So the beauty of it is that when we move from the disk, which is a simple area, to the cone surface, our program does not become more difficult. It's the same thing. Yeah, apart from the fact that you are doing your double integral here, you are integrating and integrating. So be careful of the brackets here. The brackets will kill you if you are not very careful. And you see that again, by the time you just repeat the same steps, you see that even though the values of the surface function is different, but the same thing you were doing before, because nvec is simply, where's nvec now? Nvec is a cross product of the differentiation with respect to rho and differentiation with respect to phi. So that's it. So that gives you your nvec, which you take as into dot product with the function as defined on those points, and then you specify your region of it. You specify the regions of integration, and once you finish specifying your regions of integration, bingo, you get your answer. So that is your integration on the code. Let me see what I'm doing with respect to time. Okay, good. So lastly, we go to the surface of the sphere. The surface of the sphere, which again is rimmed by the same boundary curve. We can take that the radius of this sphere has to be the square root of 2, so that this part of it will have a unit radius on the disk. So you can check that out and convince yourself that what I'm saying is true. If you are finding that difficult, just take a look at this cone. You can see that the radius of this cone and the slanting side of this cone is square root of 2. If you now let it be the radius of the sphere, you can see that everything is now the square root of 2. So that's how you get that. So if you do that again and you construct it using the spherical coordinates, which are very useful here. In this particular case, in the spherical coordinates, it is the rho that is constant. The rho is constant at square root of 2, but theta and phi are varying. And with pi over, and then the r theta is starting from pi over 4 starting from pi over 4 to pi. So to traverse the entire sphere, it goes from pi over 4 to pi. If you go from pi over 4 to pi over 2, you are only getting to the hemisphere and the surface will not have been closed. So you are going to get a wrong result. So you can see why it is very important to be able to specify your boundaries correctly. And then phi itself, theta goes from pi over 4 to pi. Phi goes from 0 to 2 pi. And then the surface normal is evaluated exactly the same way. You differentiate this function with respect to the first variable, and then you differentiate it with respect to the second variable, and you take a cross product. And the mathematical code below, that is what we do here. So you have, again, the curl of the F1, F2, F3 as defined before. And then after that, you take the variable that is the position vector on the surface, and you expand it this way. So if you have it this way, this is a vector, by the way. This is the x component, this is the y component, and this is the z component. So with that, you can now take the cross product of the derivative of this with respect to phi and the same derivative with respect to theta. Once you have done that, you have got your normal vector. With that, you can now perform your double integral of the field properly evaluated at the correct points, dot it with the normal vector, and then specify the domain of the integration. Once you specify those, again, mathematical grinds it out for you and gives you the same answer. If you want, if you can specify a more difficult surface, it can be done. It can be done, it's not hard. We can go to oblate and prolate spheres, as well as so many other figures, and go to other coordinate systems. But the idea is not going to change. The idea is that when you are not talking about the surface, you will get two variables. And if you differentiate with respect to one variable, you get a surface vector. You differentiate with respect to another variable, you get another surface vector. You take the cross product of those two, you get the surface, one surface tangent. So the first one gives you a surface tangent, second one gives you another surface tangent, and the two tangents are not collinear. Because they are not collinear, their cross product gives you the area surface vector with the outwardly drawn normal, and that is what you compute as your n vex. Even in situations where this normal vector is obvious, even when it is obvious, you continue with it and go and compute. You compute it using our formula, because it is a good practice to be able to compute it at all times. After some time, you'll be able to look at them and say, well, it is obvious what the normal is. But this normal, remember, varies from point to point. It was only on the disk that normal was constant throughout. So the normal itself is a variable. It's a variable depending on two parameters. And it will be having different values from point to point, pointing in different directions, because I think you agree with me on the surface of the cone. As you move from point to point of the cone, the normals are pointing in different directions. And the case of the sphere is even worse. The normals are always radially drawn out. And so it depends on where you are. But this formula will give it to you with the parametric way, whereby once you specify the parameters, you have the value that you are looking for. So that is a code for the sphere. Okay, that is what we will do. We will come back to some of these examples towards the end of today's class. But that's all I would say about Stokes' theorem for now. Stokes' theorem, I've stated it for you without proof. Where's the statement now? Let me just see. This is the statement of Stokes' theorem on page 34 of the slides that I'm using. The statement of Stokes' theorem is that the integral taken over the rim, the line integral taken over the rim of a field, is the same thing as the surface integral of the curl of that field. It's not just the surface integral of the field, it's the surface integral of the curl of that field. You must take the curl of the field. So you must find how to take a curl. The curl, I think it is defined somewhere in the notes where how to get the curl. Go back to the earlier part of the note. So we have used these examples to show that once a surface is ending in a particular rim, all the surfaces that are simple and positively oriented that end that rim will always integrate to the same value. That is the thing. So apart from the fact that they are related to the line integral, the fact that they are equal to themselves is also something of note. And let us see what that means. That means that if your problem is to integrate over this sphere, if the problem is to integrate over this sphere, and then integrate only over the disk, you are going to get the same answer. So why should you be integrating over the sphere? If integrating over the sphere or some difficult domain, in fact, you can just do your, if the surface rim, if the rim falls on a single plane, then integrate over the plane, which will be very easy for you. And you are rest assured that that's your answer is the same answer you would have gotten if you integrated over the complicated surface. So that is the beauty of Stokes theorem, and that is used to great advantage in analysis for engineers. So scarcely is any engineering analysis done without referring to this. So this is how you integrate in 3 dimensions, not the beyond the simple ones that you have been doing since your secondary school days. You integrate in 3 dimensions by using the gradient, divergence, and curl, and using the Green's theorem, Stokes theorem, and Gauss theorem. Okay, so we now go to Green's theorem. We can view Green's theorem as a 2-dimensional version of Stokes theorem. It's a 2-dimensional version of Stokes theorem. And Green's theorem say given 2 scalar fields, we are looking at, since we are talking of 2-dimensional, the scalar fields are variables of x1 and x2. So we are now looking at a 2-dimensional Euclidean point space now. So P1 is P1 of x1, x2, P2 is P2 of x1, x2. These functions are defined over a 2-dimensional Euclidean point space. We can form the vector field. We can form the vector field P1, E1, P2, E2. So this is now a vector field. We started with scalar fields. We turned the scalar field into a vector field. Now, the curl of this function is simply E1, E2, E3. You use the operator form ddx1, ddx2, ddx3, and then you know this one is P1, P2, 0, because the third coordinate there is 0. So P1, P2, 0. So if you get this determinant, get the determinant of this worked out, sorry, this should have been straight lines, because it's really the determinant of this. So you see that this determinant is simply the P1. If you look at this, the P1, the X2, am I sure that is it? If you want to see what happens to P1 there, take this off. And then what you have is the X. I'm seeing something that looks like an error here. Let me just be sure I'm right. If you take the curl there, E1 is the X3 of P2. But I'm no longer very certain about my. Please, can the class just go ahead and then do this determinant for me? We'll try and work it out by hand, just to be sure that I'm not giving you something that is in error. It looks like the X3 of P2, and then when you get to E2, you have the X3 of P1, the X1 of P2. Anyway, we work this out by just taking the determinant of this. I'll do that over the break and be sure. So from Stokes theorem again, we invoke this equation here. We invoke this equation here, which is the equation of the Stokes theorem. That is, you take a field, even though the field started as a 2-dimensional field, what we make it a 3-dimensional. We make it a 3-dimensional field. So that is okay. So I can see what was happening there, because okay, now I understand. This is correct, because what is happening is that the differentiating with respect to X3 vanishes because there is no X3 in the function. So that's why at the end of the day, work this out. This is what you should get. Because remember that the functions we are dealing with have only 2 variables, x1 and x2. So differentiating them with respect to x3 vanishes. So, okay, so that is, so if you take the S now as a dx1 e1 plus dx2 e2, which is the Cartesian position vector, differential position vector. So if you take that, then here you have P1 x1 x2 e1 plus P2 x1 x2 e2. That is the vector function dot the gamma, and that is equal to the line integral here. And then when you do that, when you finish doing the dot product here, this is what you get. And so this is the statement of Green's theorem. And what it remains for us to do is to just have some worked examples in it. And I think by next week, you are going to get some worked examples in it. This week, today, I'm going to give you worked examples on the domains that I discussed the last time. I have about 5 worked examples that will end this note. So we end today's lecture. We are about 5:20 now. I think what we will do is for you to go and digest where we have reached. For those of you who have not yet digested it, we are going to give you a 20 minutes break. So we are going to meet again. We're going to meet again at 5:40. It's about 5:19 now, close to 5:20. So at 5:40, which is 20 minutes from now, I think, yes, 5:40 we'll meet again. And we will look at that point, we will go and look at Gauss divergence theorem and then some of the examples on the domains that are prepared for today's class. And if you have questions, please go to the chat room. Please, I want to warn the class. Some people don't obey the instructions they have been given. I told you, send your homework assignments to your class rep, who submits them to the office. Your class rep know where to submit them. Receiving assignments from individual students is not going to work. If you want your assignments to be graded, send it the way I have told you to send it. I'm not going to open those files. I am too busy doing other things. Much of it is also on your behalf, but it's not looking at those assignments when they are not properly submitted. It's not one of the things I'm going to do. So let me see who is the latest culprit on that. Let's see whether this guy is in class. Let's see. I just got a letter from somebody from chemical engineering department. Somebody from chemical engineering department. What's his name now? He has a very nice chemical engineering. But please, if you are the person that sent me an email sending your homework assignment to me, please go give it to your class rep and submit it in the correct way. Yes, that is Damilola Akin Adamu. Damilola, it's not going to work. Take your assignment and submit like the rest of your classmates. Thank you. See you in 20 minutes time.